Hey guys, today we're going to be looking at piecewise functions. So we'll just do like a little recap of what a piecewise function is. And we're looking at the limits of these piecewise functions and the different pieces. Well, we'll talk about that in a second. But before we do any of that, I just have a question that I want to see if we can answer. And that question is, what does it mean to say a limit exists? Now, we actually covered this a couple of days ago. And I want to be very specific about the words. It's one thing to kind of understand it, but if you can spit it out verbatim, that's the best. And if you don't know what verbatim is, extra homework assignment, go look it up. Well, the answer to this question is for a limit at a value to exist, the function must approach the same y value as you approach the x value from both sides. So as you approach from the left and the right, they have to be getting to the same place. Now, the terminology for that, or the notation, is right here as follows. As you approach a from one side, then with the plus sign, remember that means from the right. And as you approach a from the other side, that's the left, that's with the minus sign, you get to the same value. Now, I got a little also fancy with at the end here, and what this is you're saying that number L is the limit. Now, this little symbol here, starting to show you some of the math symbols that we'll be using more and more. That is an epsilon, and it technically means belongs to. That's a G. So that's what that is. And that fancy R is the best I could do for real numbers. So what the heck does that mean? All in all, it's saying L is a real number. That's what that means. All right. Again, that's not really like part of the whole scope and sequence of but it's nice to start to understand and know the notation and symbols that we will be seeing more and more. All right, so here's a little picture of a piecewise function. I don't have the equation of that piecewise function, and quite frankly, it doesn't matter because I can get all the answers I need to just by looking at the graph. So the question is, find the limit as x approaches 1 of this function f of x. So here's the x value of 1, and if you see, we got a little bit what they call jump discontinuity right there. Now they call that jump discontinuity because of that gap, how from one side to the other side there's a break and you would actually jump from one function to the other, from one piece of the function to the other. All right, but let's look at the formal approach to this. Going back to what we were saying a minute ago, in order to find that function, that limit exists, sorry about that, that you have to be approaching the same thing from the left and from the right. So we're going to have to do those two things. So in the first one, as we approach from the left, that's this side of it coming on down here. As we're getting closer to the x value of 1, the y value is getting closer to 2. Now, some of you might ask, but what about that hollow dot? It doesn't matter. It's getting closer to that value. Whether it actually attains that value is irrelevant at this point in time. Now, as you approach 1 from the right, that's coming from this way, going like that. Now the the y value is getting closer to 1. Now, these two numbers are different. So what do we say our answer is? That's right, does not exist. And just to recap, yes, you can write DNE for that. All right, let's look at another one. Alrighty. Oh, I did it in the blue, so let's change. Let's get fancy. Let's go. Ooh, orange. All right. So as x approaches 2, let's look at the limit as x approaches 2 from the left of the function. So here's the left-hand side of 2. There's 2 right on down there. So that means as we're heading this way, we're reaching a y value. It also looks like 2. Now let's look from the other side. The limit is x approaches 2 from the right of the function. That means we're on this piece of it because this is the right side of 2. And as we get closer to 2, we're also approaching 2. Again, the whole hollow dot versus the filled in dot, irrelevant. Just what are you getting closer to? Now, since both of these numbers are the same, winner, winner, chicken dinner, that means that answer to this is 2. This is that L number. All right. Now, sometimes you'll have not graphs, but the equation. So you're going to treat each individual piece similar to what we've been doing for the past couple of days, or I should say last week at this point. So you want to find the limit as x approaches 2. Notice that's the same 2 as these values here on the end. That's like the dividing line. Basically, you want to find out, do these like pieces match up? So you're going to take the limit as x approaches 2 from the left. I like to do the left first of the function. All right. So let me get rid of that before that gets confusing to anybody. Whoop. Okay, that's good. Now, as you approach from the left, which rule are you going to follow? Which one comes from the left? Well, that's right. This one up here, the less than, is from the left. The greater than is from the right. That's how you're going to think of it. So you're going to actually do x squared plus 1 for the function. Now, if you recall, what we are going to do is then just plug in. The first thing you try to do with any limit, try to plug in and see what happens. Plug the 2 in, and you're going to get 2 squared plus 1, and that should equal 5. Now, we hope when we plug in on the other side that we get the same value. So the limit as x approaches 2 from the right of the function, and from the right, we'll be following the x plus 3 rule. So the limit as x approaches 2 from the right of x plus 3. And lo and behold, it's 5. So that means the answer to my initial question, the one that started it all, the limit as x approaches 2 from both sides is 5. And obviously, if these numbers were different, that's where we'd have do not exist. One more example to look at. This guy's a little 3-piecer. I'm going to tell you with the 3-piecer, the concept is the same. There's just an extra piece of information which may be useless to us. Limit as x approaches 3 from the left of the function. Well, left is less. That's how I like to remember it. And now, which one is less? Oh, there it is right there. So it's going to be the x squared. So that's going to equal 9. Let's go on. 3 from the right of the function. And the right is greater than. And that's 3x. 3 times 3 is 9. So the limit equals 9. So sometimes people say, but what about this guy? How come nothing happened there? Again, we're looking at approaching. We're getting closer from the left, from the right. We're not talking about getting there. The limit is not about what the value equals. Imagine this is you have this graph is something like this. Let's say x squared, x is less than 3. So you have probably, let's play pretend that this is 3. And here's the x squared part. And now 3x would be a line of some sort that maybe it's coming out like that. And this y value would actually be equal to 9. Well, down here at 4, you have that filled in dot. This is what the graph of this kind of might look like. Actually, it's a little bit off. That parabola would be a little bit lower. The parabola would be doing something like this instead. Okay, so All right. So then that's like, the whole hollow dot versus filled in dot. It's irrelevant information at this point in time. So don't be confused by having too much information. Just stick to what you know. Left is less than, right is greater than when you're finding the limits. Okay, bye.